Hey, I'm David Nicholson, and I'm going to tell you about some work that I did as a postdoctoral researcher in the Prince lab at Emory on whether or not simplified stimuli might change how the brain performs visual search tasks. We care about visual search because it's a real world behavior we engage in all the time. If I'm looking for the mouse pointer on my computer screen, or I'm trying to find something on my cluttered desk, I'm performing visual search. In the laboratory, as you might know, we've long used really simplified stimuli for visual search tasks. With good reason, we want to carry out controlled scientific experiments. And in these tasks, there's sort of a hallmark of the behavior that's observed, and that's described with the term set size effect. I'm going to show you some results about that, so let me define the term. So the set size is the total number of items in these displays, a target plus some number of distractors. And if a participant only needs to look at a single feature to discriminate the target from the distractors, typically you won't see any change in the reaction time or accuracy as the set size increases. But if it requires more than one feature, for example, a conjunction of features like orientation and color, like I'm showing you in the middle column here, then you will see an increase in reaction time or a drop in accuracy, and that is a set size effect. And if you think about extrapolating this to natural images in the real world, they might be made up of many of these features. And so you would expect that there'd be these large set size effects as humans try to search them. But of course, we know that the visual system is optimized to search natural images. And we can very efficiently look at a natural image and say, is there a person? Is there a car? So this suggests that the simplified stimuli we're using might actually change the strategy the brain uses to perform visual search tasks. So how could we test this idea? Well, what we've done is use deep neural networks, specifically for image classification, like this AlexNet architecture I'm showing you here, where on the left you put an image in, and then on the right it gives you back some single label, like this is a plane. And it turns out that these models have become state-of-the-art for modeling object recognition in the visual system. The deep neural networks have some nice qualities that map onto theories we have about how the ventral visual stream, for example, might perform object recognition. But for our purposes, we're less interested in mapping them onto specific brain areas and more interested in the fact that they're optimized in a data-driven way. And as other people have suggested, this can let you ask, how does the model's behavior change as we optimize it with different images? So we can take a deep neural network that was first optimized with ImageNet, this gigantic data set that people use to generate these object recognition models. Then we can adapt it to another task, for example, a visual search task using these simplified stimuli, where we ask it to classify each display as target present or target absent. And I made a Python tool to generate these displays. We could also adapt it to a different data set of natural images. For example, this Pascal VOC is a benchmark computer vision data set that's used for different tasks. And this paper I'm showing here actually used this to ask human participants to search the images and then estimate based on their reaction times a difficulty score for each image in Pascal VOC. And so the first thing we see is if you take these deep neural networks, optimized for image classification, adapt them to this visual search task with the simplified displays, we do observe a set size effect. And our core claim is that this is a result of optimizing them with natural images. That's the same result I'm showing you again, but now with these dashed lines here. Alternatively, if you just randomly initialize the weights and only ever optimize them to classify the simplified displays as target present or absent, then their performance is at ceiling regardless of the set size. And that's what the solid line is at the top here. And there's a bit of other work we've done in the paper we have in revision to support this idea that the main factor that gives rise to the set size effect is optimizing with natural images. Now, instead, if we look at natural images, a different data set of natural images, again, this is this visual search difficulty data set where you take Pascal VOC, a benchmark set of images for different computer vision tasks, and estimate a difficulty score for each image based on human reaction times while they're searching. We're gonna first ask, how do different models do just in classifying it? And we see that if we ask how well they can detect the largest object in each image, we see that the models that were first trained on ImageNet do the best. If we only train with the smaller data set of natural images we have from Pascal VOC that we use to adapt them to the task, if we just use that, then they don't do as well. But the lowest performance we see is from models that were first trained on the simplified stimuli, then adapt to this task. So this is sort of the converse of what we did before. So that suggests that in this case, being optimized with natural images helps you perform this searching natural images task. And along those same lines, we see that the performance of the neural networks is highly correlated with the search difficulty scores of the images, suggesting that it's predictive of human behavior. So overall, these results suggest to us that this mismatch between simplified stimuli used in lab tasks and the natural images in the real world might actually be impeding our ability to understand how the brain performs visual search. And what we would suggest as a way forward is to do a really fine-grained comparison of different models, a data-driven model such as ours, or a conceptual model such as guided search that I'm showing you here. Get some computational implementations, look at that, how they behave, compare that to human behavior. So thank you for listening. I'm here on GitHub as Nickel Dave and on Twitter. Appreciate your time.